Okay guys, so during our first session we covered this bar with a constant cross-sectional area, and now in this session we will go for a taper bar. As you can see, it is having length of 375 mm, one end is fixed and other end is applying load of 1000 Newton. The diameter or the area is also given. Area at fixed end, that is a A1. So we are taking this is point 1, point 2 and point 3. So at fixed end A1, that is 1000, and the other end, that is 500 mm. So first of all we have to convert this taper bar into a step bar to solve it, so that we can convert it into spring and mass system and analyze it. Okay, so see the calculation for converting it into taper bar. So we just take the average area and then created A1 section and A2 section using that average area. Clear? And the length we divided into equal parts. Okay, that is 187.5 mm for each section. So condition is same, one end fixed and free end is having load of 1000 Newton. So basically we will break it into two elements for analytical method and then create three nodes U1, 2 and 3. So at node 1 there is displacement U1, load P1 and stress S1. Similarly for node 2 and node 3. Okay, let's create a model and analyze it. Open your software, same procedure, only model will be changed. So first of all, we will create a part. Now we are again going to create a wire model, that is 1D element. For that, go to tool, parts. So this is a taper bar. Okay, or let's just give the problem number P1.2. Okay, 2D deformable wire. Okay, check the length. So the length is 375. So we'll take a double, so 800 approximate. Okay, from origin we have to draw from origin. We have to create two element for two steps. Fix the first node in sketch, then to the dimension. This is 187.5, right? Okay, 187.5 for each element. Enter. Go for second element. Provide the dimensions 187.5. Enter. So our model is ready. Click on close. Done. Okay. See, one and two. Right. Go for properties. Create properties. So material properties for problem one. One point nearly, so we'll go for dash 1.2. Take the properties. So material is same for both the section as it is same body, 2 into 10 raised to 5. Again it is steel with different grade. So go for mechanical, elastic property, Young's modulus 2 into e raised to 5. That is 10 raised to 5. 0.33. This has it. Okay. Click on OK. Then create a section. Section 1, beam truss. You already know why we are doing it, because we are creating a 1D element, planar element, 2D planar element having two nodes. Okay, so beam truss. Continue. So cross section area. Now we have two different cross section areas for two different sections, like this. For A1 it is 875, for A2 it is 625 mm square. So let's create two different sections. So this is section 1 having area 875. So put it 875 mm square, everything is in mm. Then again create second section, again beam truss with different cross sectional area, but material property is same. So area is 625. Let's put it here, 625 mm square. So this is section 1, this is section 2. Let's assign this. Check the section 1 and section 2. So section 1 is having 875 and section 2 is having area 2 620. Let's assign for first section. I will select this one only. Okay, click on OK. I will select section 1 now. Then select second, click on done. Then select section 2. So section assignment and module assignment is completed. Let's go for assembly. Go to create instance, select a part, dependent, independent, that doesn't matter right now because we are going to simple problems. Click on OK. See, it is start from origin. Now go for step. Again step. We are going for static analysis for that particular instant. So continue. Step is what? We are applying load of 1000 Newton. Clear? Go for load. First of all, we will fix this end according to our problem. See, we have to fix the point 1, point 2, point 3. Okay, so we'll fix point 1. We go for create boundary condition. Step 1, mechanical. Procedure is static, linear attribution. In that we'll select encasted. Click on continue. Select that particular node or point. Then click on done. Select encasted. Click on OK. So that end is fixed. There is no degree of freedom. All degrees of freedoms are locked for that particular point. Now create a load because our free end is loaded with 1000 Newton. So create a load. We again needed concentrated force. So select C load 1. Step 1 procedure again same, category mechanical. You have to write down this sequence in your steps. Okay, so name is what, load 1, step is what, step 1, procedure is what, category is what, and then type of selected step. Okay, so concentrate force and then write down continue. So I select this particular point from viewport and then click on done. So uniform load again in x direction, that's why I'm selecting CF1. CF2 is in y direction. We will use this CF2 during our beam problems. Okay, so for this again 1000, continue. See, the load is applied, you can see it. Okay, okay, center it. So loading is completed. Let's go for meshing. Again we have to create only two elements, that is one dimensional, two node. Okay, go for that particular part first, then go for seeding by edges. Select the particular element, click on done. By number, we already know this, so I'll directly create it. Okay, single element with two nodes. Done. Go for this one, click on done. Again by number 1, apply. So total 2 elements, 3 node. Mesh it using tool, mesh part. Yes, see, the color is changed. That means it is meshed. Select the element type for analysis. Selected it from viewport. Click on truss. Okay, so this is a type of element. You have to mention everything. Okay, element type, element library standard. Okay, then family truss, geometric order linear. After that, you have to write this thing and then okay. Okay, click on done. So meshing is also completed. That means we completed pre-processing. Now we'll go for solution or analysis and then we go for post-processing. So go for job, create job. I'll just give the problem number P1-2, continue. Okay, check the data of the model we created. If there is any error, we have to correct it. Okay, let's see if there is an error. Okay, check is completed successfully. That means there is no error. Just submit a job for analysis. Continue. Check the monitor. It will be completed within a few seconds because it is a static analysis with only two elements. So it is completed. Okay, close the monitor and check the result. This is post processing now. Okay, so go to visualization. In that, plot counters on deform shape. Okay, see these two nodes are there. Then go for first deformation. You can see the deformation. This is element 1, this is element 2. This is your node 1, this is your node 2, and this is your node 3. So this end is fixed, this end is free with load of 1000 Newton. So maximum displacement is at node 3 if you check compare your analytical results. So displacement at free end is how much? 0.00257 at free end. Okay, and at fixed end displacement is 0. Intermediate point is having displacement of, check the counter color, it is in between green and this sky blue. Okay, so you can say 8 point sorry, not 0.0000857 mm. Okay, this is how you can read the results or predict the results from the analysis. Similarly, if you go for, and you can also plot it. Okay, I'll show you how to plot it. Select XY data, or else you can create a path. Go to tool, then path, and create path. We want path for displacement, so I'll write displacement. Okay, node list, I want node. Okay, and before I'll select first this node. Where is my second node? Okay, second node. Where is second node? Just give me a second. Apologies. Okay, let's create a path so that we can trace the nodal displacement. So path, say path 1, we can trace everything using this path. Continue, say add after. This is our node 1. I'll just path create. Okay, continue. There's no point. You need to use find that point perfectly. So I'm creating a path, first, second, and third point. Okay, done. So path is created, 1, 2, 3. Okay, now we can plot according to this. Go to XY data, then field output, continue. Okay, path, continue. Okay, now we needed displacement first. So select from field output displacement, apply, okay, and just plot it. See, you can get the results. So at point 1 displacement is 0, so total distance is 375. Okay, so 375, that means in between here it is conversion. Okay, so at that particular point you can check the displacement. Now we can import this data to the Excel file to get the exact values. I'll show you how to do it. Then go to plugins, Excel utility, from Abaqus to Excel, current plot, click on OK. You'll get the exact values in Excel table. See, so basically these are your nodes. If I will say node, okay, this is your length and this is your displacement. Understood? So node 1, node 2 and node 3. Clear? See, at node 1 displacement will be 0, at node 2 displacement is this much, and at node 3 displacement is this much. Clear? Similarly, you can plot stress also. Again, go to XY data, path, continue, change the field output only. Okay, we need stress component. It is one message. Okay, and just say plot. See, where cross section area abruptly changes, stresses changes, and then throughout the area stress is constant. That means at this particular section stress is increases, and through this section it is constant. That is what graph is saying. On the other sections also it is constant. So maximum stresses are concentrated when your cross sectional area is abruptly changed, or there is a change in cross section area. Clear? Again, if you need the values, exact values, go for plugins, tools, Excel utility, then from current plot, just import it and check the Excel file. See, this is your result. Again, it is same. Nodal list and everything. Just add. Okay, let's copy this data from here. Okay, that is the end. Okay, we are concerned about this point, center point, 875. So basically this is completely, this is second, this is second, and this is third. Okay, so we'll get the average value here. Okay, this is how you can plot. You can also copy paste this data in your document file. Okay, edit these things, copy paste this properly, or you can screenshot this thing, anything, and then reaction forces. Finally, reaction force. Go for path, continue, field output, we need a reaction force. Okay, and then plot it. Okay, so at free end, so true distance along the path, at fixed end we are getting reaction force, and at free end it is applied force, that is 0. Okay, let's go. That's it. This is the end of second video, second problem. I'll upload next one shortly. Just go through it, create a step-by-step procedure, type it, extract the pictures from this video, or else you can perform it and then extract it. Clear?